Okay, last time we talked about the Diels-Alder reaction. And the Diels-Alder reaction is a concerted reaction that forms a cyclohexene. All the steps are happening at once. Pi electron's going here, it's going here, it's going there. It's a type of reaction called a cycloaddition. Cycloadditions are known for changing the number of pi bonds by 2. And they are technically reversible though it takes a lot of effort to reverse a lot of cycloadditions, meaning high heat, vacuum, to the point where the molecule would rather just decompose and become, well, ash before it actually does the reverse. But technically. So, there are other cycloadditions besides the Diels-Alder reaction. Like if you take two alkenes and heat them together, you get no reaction. But if you take two alkenes and shine them with UV light, you can get a reaction. This is what's referred to as a 2+2 cycloaddition. Where we're adding 2 carbons on one, 2 carbons on the other, forming 4. The Diels-Alder reaction is what's called a 4+2 cycloaddition. Now, why light for this? Well, that has to do with molecular orbital theory. Remember, the molecular orbitals of an alkene consist of, there's 2 of them. There's a filled one where all of them are in phase with each other, and an empty one where they are in opposite phase. This is the HOMO, and this is the LUMO. Well, the thing is, in order for a reaction to take place, you need an orbital with space in it to interact with a filled orbital. And so if we take a look at this, we have the LUMO of one alkene. That's the one that's empty. Interact with the HOMO of the other alkene. We see that the interaction is good here, but bad here. they do not have the proper symmetry. To interact. What I mean by that, they don't have the proper symmetry to interact. Well, if we take a look at the Diels-Alder reaction, here we have the HOMO, and here we have the LUMO of the dienophile. We see that shaded with shaded, unshaded with unshaded. We have the proper symmetry to react. What does the light do? Well, what the light does is it takes, here we have the molecular orbital of one molecule of ethylene. Essentially what light does is it provides energy. And when the energy matches the energy of this gap right here, essentially that light is absorbed. And when that light is absorbed, one of the electrons is promoted up into a higher level. And so what we've gone from is the HOMO and LUMO to two new ones. These are both what are called SOMOs. SOMO is short for semi-occupied molecular orbital. I wish they would have just called it semi-unoccupied molecular orbital, then we would have had SUMO, and that would have been funny. But alas, they didn't really go that way. And that's a shame. But essentially, before you shine light on the ethylene, it's what's referred to as the ground state. When you shine light on ethylene, that's referred to as the excited state. Now, some of you may be looking at the directions of the arrows on the excited state. These two are different. And this is what's referred to as a singlet excited state. This is what referred to as a triplet excited state. And the two excited states are different. They behave differently. But that's not a topic that we're going to go into in this class. For that, there's physical or organic chemistry. That's offered as a graduate class. You're more than welcome to take that as well. And that go into more of the differences between singlet and triplet states. But if you want to know, there is actually a difference. For example, singlet states are involved in what's called fluorescence. You might see in fluorescent dyes, that kind of thing, when you shine light on it, they glow. Triplet excited states are involved in what are called phosphorescent dyes. And those also glow when you shine UV light on them, but they glow for a much longer time. So they are different, but we're not going to worry about the differences between them. So anyways, you get this excited state. Now, so essentially we have two alkenes. We shine light on it, and one of those alkenes becomes excited. And essentially, the excited states are what are doing a lot of the chemistry. We have, let's call this one ethylene 1, and this one ethylene 2. The excited one, we have ethylene 2, we have the SOMO of the excited one. Can interact with the LUMO of the ground state. And at the same time this is happening, we can have the other SOMO of the excited state interacting with the HOMO of the ethylene in the ground state. And essentially the reason they can interact now is you have a filled orbital interacting with an unfilled one, and here we have a filled one interacting with an unfilled one right here. And both of them have the proper symmetry, shaded with shaded, unshaded with unshaded. And so therefore they can come together and react. And so this is a lot how cyclobutanes are made. We're not going to worry about the stereochemistry of the cyclobutane reaction. It's a little too complicated. But there is one reaction I do want to show you. Here's an example of a 2 plus 2. It unfortunately is a very common 2 plus 2. You shine light on these. The two alkenes come together. We won't worry about the stereochemistry of this reaction. Like that. And you form a cyclobutane. Now, this reaction is a very bad reaction. Essentially, this molecule is thymine. And the R group Well, that's DNA. And so UV light, what it does is it takes two thymines that are close together in DNA and binds them together. Luckily, this process is reversible, and there are enzymes that cause it to go backwards and repair the damage. However, those enzymes are not 100% effective, and some of these things occur. And what happens then is essentially it stops DNA from unwinding, or it kinks the DNA helix together and creates transcription errors, which lead to things like mainly cancer. And so tanning booths and UV light from the sun, that's where skin cancer typically comes from, is this. So, strong UV light will kill the coronavirus probably, but it's going to do a lot more damage to you in the process. So I suggest that you don't use a tanning booth as a cure for this virus. All right. In fact, you probably shouldn't use a tanning booth for a cure for anything, to be honest with you, because this is a very dangerous reaction with very serious consequences. Okay. Now, I'm going to switch gears just a little bit and talk about electrocyclic reactions. They look an awful lot like a cycloaddition reaction. So an example of an electrocyclic reaction might be this. If you heat this up or shine light on it, you get this. This is not a cycloaddition. The number of pi bonds is changed by 1. So we start out with 3, end up with 2. And the mechanism for this is electrons go here, here, here. It is a concerted process. Now, it's also reversible. Here's the neat thing about this reaction. Is if you start out with some stereochemistry, like say 2 methyl groups like there. If you heat this up, you get a molecule like this. Or if you shine light on it, Get a molecule like this. And the two molecules that you would get from heat and light, turns out they're diastereomers. I haven't filled in the stereochemistry yet. We're going to use the heat and light and molecular orbital theory to figure that out. So let's start with the heat one. So we're going to worry just about the pi system about this. And we have 6 sp2 hybridized atoms, so we have 6 p orbitals. And then each of these has a methyl group. This one's heading to the right. This one's heading to the left. Now, when we're using thermal, we're using the ground state. So we're going to be using the highest occupied molecular orbital, the HOMO. And it is pretty straightforward to draw the HOMO on these even numbered systems. You basically just look at the Lewis structure and copy it. We have a pi bond between 1 and 2. So we don't have a node between 1 and 2. We don't have a pi bond between 2 and 3, so we have a node there. Then we have a pi bond between 3 and 4. Then we have another node between 4 and 5. And so on and so forth. Okay. Now, the idea is to make that carbon-carbon bond between 1 and 6. So we need to get these two p orbitals to touch. And they need to do so they have the same shading. And so what's going to happen is these are going to rotate. And you pick a direction. Say this one rotates counterclockwise. What that's going to do is it's going to move the dark lobe inwards. Now, in order to make a bond to that, the other dark lobe has to be rotated inwards, like so, 90 degrees, in order to make that overlap between the two. And so what that does is it rotates this methyl group that way, and rotates this methyl group clockwise. So this is what's called, when one goes counterclockwise and one goes clockwise, this is what's called disrotation or disrotatory. And as a result of this disrotation, both methyl groups end up heading downwards. Now, you could have rotated the one on the left clockwise. Then the one on the right would have to be rotated counterclockwise to get the white lobe interacting with that. In that case, the methyl groups would end up as both wedges. These are the same. So the two methyl groups end up cis to each other. It's a disrotatory. like so. Okay, now let's talk about light. Light promotes an electron from the HOMO to the LUMO. And the most important one, then molecular orbital in this case, is the LUMO, because that's the highest energy SOMO, semi-occupied molecular orbital. That's the one that's going to be doing the work. And so when you're dealing with a light reaction, you want to use the LUMO. So, heat, you want to use the HOMO, light, LUMO. Heat, HOMO, light, LUMO. If only there was an easy way of remembering that. Alas. So, to draw the LUMO in, the LUMO is a little trickier than the HOMO. It's just like the HOMO, except opposite. What I mean by that is wherever there is a node in the HOMO, there isn't one in the LUMO. Where there isn't a node in the HOMO, there is one in the LUMO. So it's easier to show than to describe. So if we look at our Lewis structure, here are our pi bonds. Those are where the nodes in the LUMO are going to be. Right there. So this is the LUMO. Now when we rotate, let's say we rotate the unshaded orbital in, so we're rotating that clockwise. What we would need to do is rotate the unshaded on the right in. That would be clockwise. So this is what's called a conrotatory process in the same direction. So the methyl group then is rotated on the left. It's rotated clockwise, so it goes up. Methyl group on the right is rotated clockwise. It goes down. Now you could have rotated them the opposite way. In which case, you get the other enantiomer. So the methyl groups end up trans to each other. Now, what you should not do is memorize conrotatory and light, or heat and disrotatory. That's not how it works. It is dependent on the structure of the HOMO and the structure of the LUMO, depending on whether or not it's going to be a conrotation or disrotation. Easier method. The Woodward-Hoffmann rules. This work, these rules are laid out, granted Hoffmann the Nobel Prize in 1981. Woodward unfortunately passed away in 1979. But he still received the Nobel Prize in 1965 for other work. But R.B. Woodward, interesting guy. Read up on him sometime. He was kicked out as an undergraduate for not studying and for spending all of his time in lab, so he failed all of his classes. Took a year off, came back, and ended up taking all of his classes in a year, undergraduate classes, and getting his undergraduate degree in a year. And then he also got his PhD in a year. So yeah, look him up. Interesting character. Roald Hoffmann, neat guy as well. So let's see here. What the Woodward-Hoffmann rules are a way of keeping track of these orbital symmetries. And that you have two types of systems. You have 4n and 4n plus 2 systems. These represent the number of pi electrons. And 4n plus 2 are just ways of remembering the number of electrons, where n is an integer. So 4n is 0, 4, 8, 12, 16. 4n plus 2 is 2, 6, 10, 14, etc. And then you have two conditions, heat and light. When there's 4n plus 2 electrons in heat, it's disrotatory. When it's 4n plus heat, it's conrotatory. Four n plus light is disrotatory. 4n plus 2 with light is conrotatory. Notice they are opposite each other. Now I'm going to throw in some more terms in here. Superfacial, superfacial, and antifacial. And I have too many. Let me spell that out. Con and dis refer to electrocyclic reactions. Superfacial and interfacial refer to cycloadditions and sigmatropic reactions. We haven't covered sigmatropic reactions. We have covered cycloadditions, and we'll come back to what these terms mean in relationship to those cycloadditions. But right now, I want to focus on the electrocyclic reactions. So, know this table. It's really helpful. In fact, there is a way that you can fill out this table pretty quickly. It's a mnemonic that I have to use. So you have 4n plus 2, heat and light. And what you need to remember is the phrase 6 is tedious, where 6 electrons is thermal, disrotatory, superfacial. Thermal, 6 electrons, disrotatory, superfacial. And then from that, you can fill out the entire chart. Now, 6 is tedious might sound like it's not easy to remember, but if you replace this vowel with another vowel, it becomes a phrase that is easy to remember because it's funny, and I can't say it out loud because otherwise I'm sure I will be fired. So anyways, you never know how conservative or liberal institutions are until you test the limits, and I don't feel like testing the limits today. So anyways, just remember 6 is tedious, and now I'll give you this chart. Now, how to use this? Well, this is particularly useful in terms of ring opening and ring closing reactions. And so, let's go ahead. Electrocyclic reactions, turns out, are completely reversible. So if you say you have this cyclobutene and you heated it up, you get one product. You shine light on it, you get another product. And the way to use this is you start off with the chart. 4n 4n plus 2, heat, light, and figure out how many electrons are being moved first of all. And you do that by taking the bond that's actually breaking and you move it. That goes to there, that goes to there. 2 arrows complete the circuit. 2 arrows equal 4 electrons. And so, just to kind of finish up this one, since we're talking about an electric cyclic reaction, I'm just going to throw in the cons and this into the chart. 4 electrons right here. And when it's thermal, then it's a conrotatory process. So, how to use that? We make a little cartoon. This dot is that carbon. That dot is that carbon. We have that's a wedge, so we have the methyl group going straight up. The blue one is dash, so we have the methyl group going straight down. Now a conrotation means they're rotating in the same direction, so we pick a direction, like this methyl group, we will rotate 90 degrees counterclockwise. That means this methyl group has to be rotating 90 degrees also counterclockwise. And so we end up getting the 2 methyl groups, one going to the left, one going to the right. So you get that. Now you could have just as easily rotated it the other way. So this went clockwise, and this one has to go clockwise. In that case, you get the methyl groups heading inwards. And that gives you this right here. Sterically unfavorable. So it chooses the outside ones. Light. We have disrotatory. So again, we start with our little cartoon. And since it's disrotatory, if we move this one counterclockwise, the other one has to be moved clockwise. And so we end up with this situation, where the methyl group attached to the red carbon is to the left, and the methyl group attached to the blue carbon is to the left. So we get that. Now we could have also gone, switch them, goes clockwise and counterclockwise, in which case we get this, and we get the same answer. Okay. So there's more to that, but we'll have you practice on the problem set with that. Okay. So, the Woodward-Hoffmann rules on cycloadditions. We had two cycloadditions. We had a 4 plus 2, that's just the Diels-Alder reaction. It's under heat. And we had the 2 plus 2, that is light. These are what are known as superfacial reactions. In the case of the light, you have a SOMO reacting with a HOMO, and we have a LUMO reacting with a SOMO. And so essentially we're taking the top of one of them, same face of this one and the same face of this one, and react them together. And that's the same way with cycloaddition, the Diels-Alder reaction. We have the top of one molecule interacting with the bottom of the other. That's what's called a superfacial interaction. And most superfacial interactions are allowed. The other deal for superfacial is an interfacial reaction. And an example of an interfacial reaction is this, reacting what's called a ketene with an alkene. And it's not done under light conditions, it's under heat, and it's a 2 plus 2. This is what's referred to as an interfacial reaction. We have had an interfacial reaction before. That's a Wittig reaction, is an interfacial reaction. and it's also a cycloaddition, followed by an immediate opposite of the cycloaddition, a cycloreversion. And we'll get to the interfacial reaction. This will be the topic on Wednesday, along with sigmatropic rearrangements.